Okay, so as chief guest gave an interesting talk where he mentioned 6 qualities that they look for from somebody who comes into industry. That was interesting. He call them the 6 C's because they all start with C. So, the first thing that he says they look for is common sense. They are not looking for geniuses, but they are looking for people who can apply simple common sense to solving problems. So, he says that is a very important characteristic. Then he mentioned curiosity, that you should not be indifferent to your surroundings. Whatever you see when you come into industry, if there is something you do not understand, they expect you to ask and find out what it is. It is very easy to spot curiosity in somebody. It's a person that goes around asking lots of questions about everything around them. And so, that again he says is a highly valued quality in a new employee. Then he mentioned chemical engineering basics. If you are coming in as a chemical engineer, you have to know your stuff, that is obvious. Then he mentioned commitment, that you should not give the feeling to people around you that you are only there for a short period of time and then you are going to go somewhere else, that this is just a stopover in your career journey. Even if that is true, it is not something you want to advertise. You should at least make it appear that you are going to be there for a long period of time, so that they will take you seriously. Communication, again, that is something we have talked about a lot. It is important not only to have ideas, but to be able to communicate your ideas to others, so that they understand your value to the company. And then customer focus. He said right from day one, they kind of want you to show that what you care about the most is not what is happening inside the company, but rather how it affects the customer. That kind of customer focus is something that is obviously lacking in an academic setting, because you do not even know who your customer is. But in industry, there are internal customers. If you work in research, development is your customer. If you work in development, manufacturing is your customer. If you work in manufacturing, QC is your customer, right. So, and there are external customers, people who actually buy the products that the company is making. So, customer focus is another thing they look for. So, the 6 attributes he mentioned, starting with C, are curiosity, cost, chemical engineering basics, communication, commitment, and customer focus. He says they expect all employees to have these. So, customer focus is a good lead into the next topic we are going to talk about, which is quality. A lot of people think of quality as something that you measure internally. At the end of your process, you can do some inspection, and let us say that you find out of 100 products you test, if 99 are good, then you say that your process yield is 99%. And does it mean that you have a high quality product? So, you have to differentiate between process quality and product quality. Process quality is what you measure at the end of the process. You can measure process efficiency, you can measure process control, you can measure process optimization, all those things. But the customer is not buying your process. The customer is buying the product that you make from your process. So, the only quality that really counts is your product quality, and even that is not based on your measurement of product quality, but rather the customer's measurement of product quality. You may think that you are supplying a very high quality product, but the customer may not agree with you, and if there is a disagreement, the customer always wins, because the customer will just stop buying your product and you go out of business, right. So, the first thing to realize about quality is that it is an external metric. It has nothing to do with your internal measurements. You are just fooling yourself by doing any quality tests in house, because it is completely irrelevant to the market. But quality is certainly a very important parameter in process optimization. When you are optimizing a process, again you have to keep the product in mind. Process optimization does not mean having the best possible process. it means having a process that delivers the best possible product. There is a difference between the two. The product focus is a customer focus. Process focus is something very internal. It is very selfish in a way. So, you have to understand how process quality affects product quality. You can certainly fine tune process quality in order to improve your product quality, but ultimately product quality is the one that really determines whether you stay in business or you go out of business. So, Taguchi is actually I think there is a slide on Taguchi. Dr. Genichi Taguchi is a Japanese guy, born 1924, almost 100 years ago. I think next year they are going to be celebrating his centenary. He was a director of Japanese Industrial Technology Institute, executive director American Supply Institute, winner of Deming prizes in Japan. Deming is a quality prize, right? You may have heard of it, for 4 years, over 3 decades. Received Blue Ribbon Award from Emperor of Japan in 1990, Schuhart Medal from American Society for Quality Control 96, honorary member of Japanese Society for Quality Control, American Society for Quality Control, inducted into Automotive Hall of Fame. He introduced many quality measurement methodologies, and the US actually picked up on these even before the Japanese did. Now, it is very interesting. Deming was obviously a Westerner, but the Japanese bought into his philosophy before the West did, whereas Taguchi was the exact opposite. He was a Japanese, but his ideas permeated American and European manufacturing much earlier than the Japanese picked up on it. So, how did Taguchi define quality? He said quality is the financial loss to society after the article is shipped. Well, unfortunately, Japanese are not very good at English, so it does not translate very well. I think the original statement in Japanese actually made a lot of sense. Another way to look at it is quality is the avoidance of financial loss to society after the product is shipped. So, the idea is if you ship a defective product which the customer is not happy with, the customer is going to want to return it, or they are going to want you to repair it. So, there is cost involved, but that is at an individual customer level. But if you look at a defective process which is producing many defective products, then the financial loss is not to a single customer or to a single industry, but it is to society as a whole. So, he said every time you ship a defective product, a low quality product, it involves loss not only to yourself, to the company, but to society as a whole. And there are 2 categories of loss that he mentioned. The first is losses due to harmful effects to society. So, he said even if you ship a perfect product, but it pollutes the environment or causes safety issues, it is a loss to society. Example is cigarettes, right? There are industries making cigarettes. They may have all kinds of quality controls, and they may be shipping the best quality cigarettes, but they are actually harming society, right? Because every cigarette that is smoked is potentially leading to cancer, which is leading to medical problems, medical costs. The second category, which is more relevant to what we are going to talk about, is losses arising because of excessive variation in functional performances. When you make a product, it is supposed to have certain characteristics, and the more it deviates from these characteristics, the more defective the product is. So, a high quality product will always will be at its ideal value for all the important performance characteristics. So, the Taguchi philosophy, basically he said reduce variation, find this ideal value for every parameter of the product, and make sure your production always results in a product that is as close to this ideal value as possible, because that way there is lower loss to society because of defective products. We call this economics of improved quality. How do you do that? It has to be done during the development stage. The product that you develop has to be robust enough that it can withstand variations in process conditions and still maintain quality. this whole concept is called robust design, and we will talk about that some more, but that is where chemical engineers can add a lot of value. By the time you try to achieve quality in manufacturing, it is almost too late, because the only way you can do that is by doing a lot of inspection and screening or throwing away bad product and only shipping good product to customers. Obviously, that is not the best way to do things. I mean, it is a lot of material loss, it is a lot of time loss, because somebody has to sit and do this inspection where they could be doing more productive work. So, it is up to engineers to develop products that can reduce variation and that can also withstand variation in parameters. There are two areas that Taguchi addressed. One is online quality control and the other is offline quality control. Online quality control, every industry does that. I mean, if you have ever done industry tours, I am sure they have taken you into their QC lab. They will show you reams and reams of data. It used to be paper, now it is all digital, but there is just a lot of data that they have taken. They will show you whatever process parameters they have monitored, they will show you trend charts, they will show you control charts to prove that their process is under control. It is called statistical process control methodology, but Taguchi's argument is SPC is not sufficient. It just says the process is under control. It does not say that the process is centered around its ideal value. So, we will show you what that means. Offline quality control is building quality into the design, right. Again, designing so that variability is minimized, and designing so that even if there is variability, the product continues to function at a high quality level. This can have a very high impact on cost, because you are doing quality optimization early in the product life cycle. As I said, once you have ramped up into production, it is very hard to do any fine tuning to get better quality, or even cost. So, anything you want to do to improve quality, do it very early in your manufacturing process. Okay, so let us look at some examples. These are 4 examples of output from 4 different factories. LSL stands for lower spec level, USL stands for upper spec level. So, I have 4 different distributions, right. In all 4 cases, the process mean is between the specification levels. Well, in case 3, the process mean is right at the lower specification level, but in 1 and 2, the process mean is well within the specification limits. Of these 4, which factory would you say has the highest quality level? 1, 2, 3 or 4? Or are they all of same quality, or is one better than the other? Does anybody think 3 has the best quality? 1, 2, 4? Okay. The correct answer is 4. Why? Because the variation is minimal. It is not so important that it is important that the process is centered around the mean. T stands for target value. So, in at least 3 out of the 4 distributions, process is centered around the mean, and normally that would be considered good. But then if you look at the variability, in cases 1 and 2, there is a fairly significant percentage of product that is going to fall outside the spec limits, right. The tail is very broad, whereas in case 4, all products are going to be within spec, and not only that, it is a very tight distribution around the target. So, all products are not only going to be meeting spec, they are actually going to be very close to the ideal value or target value. So, factory number 4 will be the benchmark for all the other factories. So, another way to ask this is, if quality is conformance to spec, meets customer requirements, fitness for use, and then there are 4 manufacturers, all with 0% defective products, all produced to the same specs and the same price, which one would you select? It's kind of a trick question. The answer to this is there is not enough data. What you need to see is the kind of distribution curve that I showed in the previous slide. conforming to spec is not sufficient. Cases 1 and 2 conform to spec, but we said that is not good enough, right. Meet customer requirements, as long as it is within spec limits, it is meeting customer requirements. Fitness for use, again, as long as it is within spec limits, the product is fit for use. However, even visually we were able to tell that 1 and 2 are not as good as 4. So, again the same chart, if A, B, C, D and D, now you actually get to see the quality distribution chart, you can easily make the call that D is the best. So, what you need to see before you can assess the quality level of a manufacturing line is the raw data. It is not enough if the supplier just tells you all their product meets specs, it means absolutely nothing. So, try to move your process towards the ideal value. So, A, B and C again all have process means that are right at the center, target value, but A has a very broad distribution, B has a tighter distribution, reduced variability, C has minimal variation, very tightly clustered around the target value. So, by reducing variability you improve quality, and by improving quality you reduce cost, because what is going to happen in the case A, there is some product which is falling outside the spec limits, they are going to get rejected, you are going to have to rework them, or they somehow escape into the field, it will fail in the customer location, they are going to send it back, all of that is going to involve cost. In B, again you are getting so close to the spec limits that you are going to have to take some action to bring it back inside, that involves process cost. C is high quality and low cost. So, Japanese actually taught quality to the West, I mean Europe, US, they all picked up that quality strategy from Japan. But if you look at how Japanese quality has evolved over time, for a long time from the 40s to the 70s, they were, well, at least the 60s, Japanese were ensuring quality simply by inspecting. They will inspect every product and they will throw out products that were defective. So, they never shipped bad product to customers, and as I said, quality is a customer metric, right. So, if the customer never sees a bad product, they are going to say you have very high quality. The problem though, the Japanese were incurring very high cost because of all the inspection they were doing. So, clearly not an ideal strategy to follow. And then starting in the 50s and still continuing, process control. By doing statistical process control, you do not wait for defects to happen. As soon as you see a drift in your process towards an out of control condition or an out of spec condition, you make some changes to your process to bring it back to the mean value or the target value. So, that is a much better process to improve quality. And then starting in the 70s, 80s, 90s and continuing till now is robust design. Do not try to fix the problem in production, try to have a design that automatically gives you a high quality product, and that is where chemical engineers can add value. I mean, quality by inspection, even by process control, you do not need chemical engineers to do, you just need some trained operators with high school education, they can do it, right. In one case it is just sitting and inspecting something and saying yes, it meets quality requirements or no. In the second case it is just a lot of data analytics, looking at reams of data and deciding whether the process is stable or not unstable. But the last one, robust design, by doing DOE stands for design of experiments. In order to come up with a robust design, you have to do well designed experiments. The experiments have to be well planned so that you catch all the major effects of relevant parameters. So, that is where we can add value. And so, the influence of chemical engineers on product quality has really taken off in the last few decades because of this focus on robust design. Another way to look at it is Early on, quality control was done by inspection, then by statistical process control, then by improved designs, quality through design, integrated design and manufacturing. Even if you are doing improved designs, unless you have manufacturing involved right from day one, working with design hand in hand, it does not work well, because the design function may come up with something and tell manufacturing go make this, but then there may be a lot of practical problems in making that design, right. Whereas if design teams and manufacturing teams can sit together from day one and design the product, manufacturing it will be very easy. So, that is the trend that we are seeing in quality control. So, in the design cycle, what are the different stages? There is something called systems design, something called parameter design, and something called tolerance design. Systems design is, as the name says, you kind of look at the entire product as a system, a very high level view. It enables you to establish some basic engineering and design concepts. Parameter design is identification of critical dimensions and other parameters, properties of the product, and you start doing statistical design and sensitivity analysis. Sensitivity analysis is another important tool in design, where you look at the effect of various input parameters and operating parameters on output parameters, and you can do it very precisely and very mathematically. So, statistical design and sensitivity analysis start in the parameter design stage, and then tolerance design is the next stage, where based on the results from the parameter design exercise, you establish what are the acceptable tolerances. A tolerance is basically a lower spec limit and an upper spec limit. So, these tolerances are established through statistical techniques and through carefully thought out experiments. So, these are the three stages, and engineering expertise is required in all three. So, we are in business as chemical engineers. In designed experiments, what are the objectives? How does it flow? First thing is, when you are designing an experiment, and this is true even for your thesis work or project work, you have to define the objective of the experiment. Design the experiment, you have to identify what are the pertinent factors, and then what are the settings you should test them at. What is the minimum, what is the maximum, and by the way, any designed experiment should have at least 3 levels for every parameter, right, because that is the only way you can catch non-linear effects. If you only test parameters at 2 levels, the only thing you can do is establish a linear dependence between them. Assess available resources and select appropriate design. If you have 10 parameters in your system and you want to test each one at 3 different levels, you will really have to do 3 to the power 10 experiments to catch all the various effects. Clearly, you are going to be resource constrained, which is something you cannot do. So, you have to be picky based upon availability of resources. Select an appropriate design, conduct the experiment, analyze the data. So, a lot of statistical analysis is required, and based on your data analytics, come to some conclusions, formulate some recommendations, but then you have to do a confirmation run. So, let us say that based on up to that stage, by analyzing the data, you have come up with an optimum set of parametric conditions. You will have to run more trials using this optimum conditions that you have identified to confirm that yes, this combination of parameters gives me a better product than what I got for all the other combinations of various parameters. Even then, once you have done the confirmation and you have started production with this optimum set of parameters, you still have to monitor and make sure that whatever results you obtained during your experiments are valid when you ramp up to production scale. And finally, you have to have some understanding of the physical model. This cannot be a completely empirical exercise, because if you do it simply as a data driven algorithm, there will always be surprises, because you may come up with some conclusions based on, let us say, million data points, but then the million and one data point may give you a completely different result, right. So, unless there is a theoretical basis, unless there is a fundamental understanding, you are always at risk that the next data point you gather may completely invalidate all your current assumptions. So, what were Taguchi's contributions to this robust design? Again, the philosophy, the objective is reduce variability and maintain process on target, minimize departure from the target value because it is lost to society, have a design that is insensitive to variability. Once you begin production, there is always a push to reduce cost. So, manufacturing may decide that this particular component that goes into the product is too expensive. There is this other supplier local who can give me the same component at half the price, right, and they may just switch. The product has to be designed so that it can still function very well even after you introduce this low cost component instead of the original high cost component. Again, the methodology is robust design is achieved by experiments, well designed experiments that can include factors like noise, signal to noise ratios. The one difference that Taguchi introduced, have you guys done DOE? I mean designed experiments? Do you know about orthogonal experiments, all that kind of stuff? Have you taken, I think if you have taken experimental techniques or mathematical methods, you should have probably covered DOE somewhere. But there is a way to do it that mathematicians like, which is to treat all parameters equally. If there are 5 parameters in your system that affect your output, they will design an experiment that involves all 5 parameters and they will test them all. Taguchi said you have to use your engineering knowledge. You should know as an engineer whether all 5 parameters are important or only 3 of them are or only 4 of them are. Then only test those 4, throw out the 5th one, right. So, he also said most of the time the effects are first order. So, again if you have 5 parameters, the effect of each parameter on your output quality is going to be more than interactive effects between the parameters. So, he said most engineering problems you only have to worry about first order effects, not about second order effects. You understand the difference, right? For example, if you have temperature and velocity as 2 of your parameters, you can look at the effect of varying temperature separately and the effect of varying velocity separately. But you should also look at both of them varying concurrently, right? That is what I mean by second order interaction. Taguchi's argument is in most engineering problems such second order effects are less important than first order effects, which obviously simplified the design of the experiment. So, what are the key issues in robust process and product design? You have to reduce variability, but you have to do it efficiently and economically. I mean if you throw enough money at any problem you can solve it, but that is not the smart way to do it. You have to come up with a solution that you arrive at with minimum cost, but maximum effect. Migration of the design from development lab to manufacturing factories. As I said, something that looks fantastic in the development stage in a pilot line may crash and burn when you move it to manufacturing. So, you have to validate your design when you move into manufacturing. There is always time, cost, materials and manpower needed for development, and industry does have some resistance to it. They only look at people who work in manufacturing as really being direct contributors to revenue, because they are making product and the product is being sold. People who work in development are always viewed as these scientists who are just playing, right. So, you have to continuously justify your existence. If you get into the development organization, you will have a lot of fun, but you will have to constantly justify your existence. Adaptability of designs to changes in engineering tolerances. Again, robust basically implies that the product has to be able to withstand minor variations in virtually every parameter that affects it. Some of these may be controllable variations, some of them may be uncontrollable, also called noise, right. So, noise factors very expensive to control, very hard to control, and there are 2 types of noises that Taguchi defined. Outer noise is variation in operating environments and human factors. So, if you are making a product and it is a manual process, so there are a lot of people in the line putting things together and so on, there is going to be an inherent variability, because humans can never do anything the same way 2 times in a row. There is always going to be minor changes in the way they do things. So, there are going to be human factors that contribute to variability, that is called an outer noise. Even if the line is completely automated, so you have robots doing it, there are still going to be minor variations even in how robots put things together. Even a robot cannot follow the same instruction identically every time. There are going to be minor variations, and it could be as simple as, if the temperature changes in the environment or humidity changes, the robot will be affected by that, right. Inner noise is something that is built into the manufacturing line. For example, if you have some equipment that you are using to make your product, but it has been around for 50 years, it is going to start deteriorating, and as the equipment deteriorates, there is going to be a variation in the quality of the product you are making, right. And then there is also something called between product noise, which is manufacturing imperfections. So, even if there is no outer noise, even if there is no inner noise, there will always be noise present, because manufacturing is a process, and a process by definition cannot be run the same way identically every time we make a product. All you can do is try and minimize the variations. So, what do you do? How do you handle this? You select your settings for controllable parameters so as to minimize impact due to uncontrollable parameters. You just have to live with it. You have to assume that there is going to be, as a net of all this, some 5% variation day to day in your production, but you design the product such that it can withstand this 5% variation. That is where robust design comes in. So, the Taguchi definition of quality is that product characteristics that measure performance relative to customer requirements. So, if your product parameter exactly meets customer requirements, then you have a high quality product. If it meets or exceeds, certainly if it is even better than what the customer expects, great, you have a very high quality product. But if it is anything less than what the customer requires, then it does not have sufficient quality. Quality is related to loss to society caused by a product during its life cycle. A high quality product causes minimal loss to society, and loss once again is loss of product function or properties, which means it has to be replaced, time, pollution, noise, all of these cause loss to society. Example is fuel efficiency of a car. If you buy a new car, on the windshield you will see something about how many kilometers per liter you get, right. Suppose you buy the car, the windshield says 24 kilometers per liter, and you get exactly 24 kilometers per liter. Are you happy? It's somewhat relative also, because you may know somebody, your neighbor or a friend, who is driving a different model or the same car, same model, but he is getting, let us say, 26 kilometers per liter. You are not going to be happy, right. Now, you take the car back to the dealership and say, I am only getting 24 kilometers per liter. What are they going to tell you? It meets the spec, that is what it says on the windshield, that is what we are giving you. But will that company stay in business for long? No. They have to recognize that there is variability in their product, that the car they are building in some cases is giving 26 kilometers per liter, and in some cases it is giving 24, and actually if you extrapolate, you should expect that they will be making some cars that are giving less than 24, if you take a sufficiently large sample size, and similarly they are probably making some cars that is giving more than 26, right. So, unless they have this understanding of the statistical distribution of their product quality, they are not going to give a good answer to the customer. The correct response would be to say, yes, we understand that even though it is meeting spec, you are not happy because you know that there are similar products that are having higher mileage. So, bring the car in, let us work on it and we will fix it, right. That makes the customer happy. But then there is cost, right, because now the car dealer has to absorb the cost of doing all that rework. If they had made the product good from the beginning, so that this variability is not there, if 24 is your spec limit, what should be your target value roughly? Any idea? It should be 24 or 23, 22, 21? should be something much less than 24, I mean much more than 24, sorry. If your specification is to give 24 kilometers per liter, your process for making the car should be such that on average you are making 26, 27 kilometers per liter, so that you can meet that specification with less than 0.00001% defect rate. So, this difference between a spec level, control level and target value, that is very important to understand. So, one definition of quality is what we call a goalpost definition. You have a lower spec limit, you have an upper spec limit. As long as it is within these specification limits, it is a good product. This is a goalpost definition, right. But what it does not reflect is the customer satisfaction. Again, TVs, you have a TV, your neighbor has a TV, let us say we both have the same TV. Your TV quality, picture quality is okay, but your neighbor's quality is much better. So, again you take it in and the TV guy inspects it and says it is meeting all the specs, so it should be fine. But it is not, it is not as good as the same model that is purchased by your neighbor, right. So, we do not want a TV that is built to spec, we want the best quality TV. So, the other definition of quality is based on SPC. Statistical process control says, let us say your target is somewhere in the middle, you establish a lower spec limit and an upper spec limit and you let the process vary between these, well not even spec limit, you can even call them control limits, right, whatever you want to call them. And based on SPC methodology, as long as you do not exceed the specs or control limits, you can continue to ship. But is that a good quality product? Compare it to the line below, the Taguchi methodology says that is fine, but then your specification limits have to be much closer to the target value. Even the smallest deviation from the target should be cause for concern. And if it goes even slightly above this very narrow band around the target, reject, rework. That way initially your cost may be high, you may be reworking a lot of product, but you are keeping the customer happy, they are going to be placing orders for your product, and eventually you should be able to use your robust design methodologies to improve your product, so that you start rejecting fewer and fewer products, right. So, the whole Taguchi methodology is focused on staying as close to the target value as possible, not the control limits, not the spec limits, but the target value. So, the Taguchi designed something called a loss function, it is called the Taguchi loss function, which recognizes a customer's desire to have best possible product at consistent quality, and any deviation from this target value will cause a loss to society. So, this could be production costs, cost to customer due to repairs, scrap and so on. So, this curve that he came up with is called the Taguchi loss function. He says if your product is exactly at its center point, right here, at its ideal value, there is no cost to society, there is no cost to your business, there is no cost to customer, because it is perfect quality. But as soon as you deviate even slightly from the target value, you start incurring cost. And he basically said it is a parabolic profile. As soon as you deviate even slightly from the ideal or nominal or target value, your cost starts to go up rapidly. Cost again is, you can also say it is customer dissatisfaction, right. It is a customer dissatisfaction index. And he defined it mathematically as L equals k times y minus m squared, where L is the loss associated with the characteristic value y. So, it is a loss associated when you move away from the nominal value. M is that best value, right. In the previous slide, this is m, this is y, this is m. So, y minus m is the deviation from the ideal value, and he basically said the Taguchi loss is proportional to y minus m squared with a constant k. The constant k can be estimated if you know what the replacement cost is when you are at the upper spec limit or at the lower spec limit. So, k can be estimated, it is a constant. So, the key here is the more you deviate from your ideal value, the greater will be the customer dissatisfaction, and therefore, the greater will be the loss to your company and to society as a whole. Now, this is for a general distribution, but there may be distributions where lower is better. For example, emissions, right, again automotive emissions, you want it to be as low as possible. In that case, m is 0. So, L is equal to k y squared. In some cases, higher is better, mileage, fuel mileage. In that case, the loss function is k times 1 minus y the whole square. That is for a single part. If you have a very large number of parts, you can define an average loss per part as L equals k times S squared, which is a variance around that average y average, plus y average minus m the whole square. Okay. So, this is the loss function for a population of parts having a certain variability built in. So, how do you calculate this constant, the k factor? You have to determine the cost of product replacement at some point x away from the target. Again, the upper spec limit, lower spec limit, you know how much it is going to cost to replace the product because it is exceeding the spec limit. So, from that you can actually calculate k. Once you know k, you can construct this parabolic loss function curve. The key assumption in the model, we are assuming it is a parabolic curve. Does it always have to be the case? This is based upon practical experience that as you move away from the target value, your pain keeps increasing. So, it is at least a square dependence, maybe it should be even more sensitive, but square dependence seems to capture customer sentiments reasonably well. So, anyway, this is an example of how you calculate the loss coefficient. If it costs you $25 to replace a product when the measurement exceeds the spec limit, then k equals 25 by 5 squared or $1. So, the Taguchi loss function basically says to minimize loss to society, center the product characteristic. Whatever measurement you are doing has to be right at the center all the time, and that is a responsibility of production. It is a day in and day out job. If necessary, they have to constantly tweak the process so that they keep bringing the process value back to its ideal value. Variance of that particular characteristics must be reduced. That becomes both product engineering as well as process engineering responsibility, and it should be done in the design stage, robust design and all that. Again, controllable and uncontrollable factors can contribute to this loss. I mean, there are many other loss function formulations. There are asymmetric quality loss functions, lower is better, higher is better. As I said, for example, waiting time for service at a fast food restaurant, you want lower, right. So, in that case, your quality parameter has to or your loss parameter has to reflect that. Higher is better, fuel economy. There are also quality loss functions that have very different shapes. For example, let us say you are getting some soft drinks or a juice or medicine. A small deviation from the target value does not create a significant loss, but it is not negligible, but too much or too little of an ingredient can cause a large loss. I mean, a soft drink, if it tastes slightly off, you do not care so much, you just drink it, but if you see a big difference, you are not going to be happy. Medicine is even more so. If you take something like product delivery time or customer service, it is very asymmetric, because if product is delivered earlier than you expect, you are happy, right, whereas if it is delivered later, you are unhappy. So, it is a very asymmetrical distribution. So, even though the target value there may be 10 minutes for delivery, if you actually get it in 8 minutes, you are not going to complain, but if you get in 12 minutes, you are going to complain a lot. So, there are these asymmetric distributions as well. Air pressure in auto tires. If you have too little air, it is not good because your car is not going to get the mileage it should, but if you have too high air pressure, you can have a tire blowout, right. So, the results can be much more serious. Again, asymmetric, and there can be insensitive regions also, small variations you may not even notice, whether you have 32 pounds pressure or 31 pounds pressure, who cares, but 32 to 20 you will care. And then there are asymmetric distributions with zero loss in the insensitive regions, blood pressure, blood cell count. Doctors are okay as long as the deviations are minor from the target value, but if they exceed a certain number, they want you to take action, right. So, these are examples of asymmetric. So, there are many formulations of the Taguchi losses. It is a big research area to take a look at different manufacturing processes, different products, and to try to define appropriate Taguchi loss functions. So, in summary, what did Taguchi contribute? He sensitized design and manufacturing engineers to the importance of the target value. He said forget about specification limits, forget about control limits, you have to focus on the target value, the ideal value, never deviate from it. And he quantified the cost impact due to departures from the target value, because otherwise people are not going to listen. You have to convince them that if you do not make the product exactly at its ideal value, you are going to suffer for it financially, then people listen. He emphasized the need for well designed experiments to optimize product design, process design, identified uncontrollable factors and a strategy to deal with them, basically by saying control your controllable parameters so well, or design your products very well so that it is not sensitive to the uncontrollable factors. So, basically he provided the entire framework for high quality design. That is why he is considered like the father of process quality. But if you think about it, what is the downfall in all this? Do you think this is the ideal strategy for quality, or do you think there is something missing here? See, for example, he says process should always run at the target value, right. Let us say actually measurements are deviating from the target value, then what do? You have to make some adjustments, you have to go and tweak some parameters, you have to fine tune some machines, you have to replace some tools. All these actions cost money, right. Isn't that a cost also? You are improving quality, but you are also increasing the cost of manufacturing. Don't you have to take that into account also? If you are really trying to optimize the entire process, including cost, not just quality. I think the Taguchi approach is completely focused on maximizing quality, which is fine, but that is not the real world. The real world says you should optimize quality, but not at the cost of cost, right. So, what do you have to do? Taguchi has defined cost of quality. He says if you deviate by x from the target value, it is going to cost you something x squared. You have to come up with an estimate for the cost of manufacturing. Suppose I try to always manufacture my product at this ideal value, how much is that going to cost me, as opposed to letting the process vary so that there is some deviation from the target value. That is an interesting trade off, right. Then cost of manufacturing has to be compared against the cost of quality, and then the entire framework has to be optimized. So, we will stop at this point. In the next class, we will look at how we calculate this cost of manufacturing and then combine it with cost of quality analysis to arrive at an optimum overall cost, okay. And we will look at some case studies also. Okay, so see you tomorrow at 10 o'clock. I think Mr. Srinivasan will also be back tomorrow from his travels. He may come to class. Any questions? Quality is something that is very important for you to understand. It's one of those things that industry people take for granted. They don't realize that in most academic curricula, quality is not even covered. It's not something that's part of what we study. Even statistical methods of process control are not covered. So, and that is just the beginning of quality control. So, it is something you should read up on your own before you go for interviews. If you can show that you have some familiarity with quality metrics and how to optimize quality, you will impress people in industry because they know how important that is. Okay, so see you tomorrow.